Welcome to Hartman Math. Today we're going to look at multiple angle formulas. Prior to that, a review in our warm-up of some of the early stuff in Chapter 5. Go ahead and pause here and work through the 4 problems. All right, number 1, so we got sines and we've got cosines and no way to factor out. So we're probably going to need to square both sides so that we can utilize a Pythagorean identity. So squaring both sides, and then there's our Pythagorean identity. Change everything in terms of cosines, as we're not going to be able to change that one. So this becomes 1 minus cosine squared x, and then if we set it equal to 0, we're there. Factor out a 2 and a cosine x. So cosine x equals 0, cosine x equals negative 1. Where is the x coordinate 0? Straight up, straight down. Where is the x coordinate negative 1? Straight left. Now in terms of checking, remember we squared both sides, and that potentially introduces extraneous solutions. So if we go back up here, cosine of pi over 2 is 0, plus 1 is 1. Sine of pi over 2 is also 1. That one works. 3 pi over 2, we get 0, plus 1 equals negative 1. That one does not work. Pi, so we get cosine, that would be negative 1 plus 1 is equal to 0. That one works. All right, for number 2, even though we're still solving on 0 to 2 pi, we do have a multiple angle problem. So isolate cosine 2t. And then we'll say 2t equals. Now we're talking about cosine being positive, so quadrants 1 and 4. Whereas cosine is the x coordinate, so short on the x and then long going up. So that's going to be our pi over 3's. Pi over 3, 5 pi over 3. Divide by 2. Remember, don't forget our plus 2n pi's. Again, because it's a multiple angle problem. All right, plug in a 0. We've got pi over 6. Plug in a 1. We've got 7 pi over 6. If we plug in a 2, we're too big. Plug in a 1. Plug in a 0. 5 pi over 6. Plug in a 1. 11 pi over 6. And those are our solutions there for number 2. All the solutions here, it's all one function, so we should be good to go. Let's get it equal to 0 since it's quadratic, and then we can explore factoring. And we can factor. So secant x is 1/3, secant x is negative 2. But since we're not very familiar with those, maybe we could flip them and say cosine x equals 3, cosine x equals negative 1/2. I don't think that can happen. If we remember our cosine graph, the highest that it went was 1. It can never get to 3. If you try to do inverse on your calculator, it's probably going to say some sort of an error, domain error, or something like that. But this one we can do. In fact, we don't even need a calculator. That's a unit circle value. Quadrants 2 and 3. Find all solutions. So we're going to want the plus 2n pi. Kind of similar to the one we just did. Pi over 3's, but now 2 pi over 3 and 4 pi over 3. That would be an error. So we would want this to be 2 pi over 3 plus 2n pi and 4 pi over 3 plus 2n pi. My error. Don't forget n is an integer. All right, number 4, verify. A little bit tough to figure out which one's the more complicated side, but in terms of maybe thinking at some point, possibly going in terms of sines and cosines, addition is going to be harder than multiplication, so I think we might want to work over here. But keep in mind kind of what our goal is. If we do that, this is essentially 1 over cosine x, 1 over sine x. All right, so let's work on this side. And let's go ahead and try that, sines and cosines only. All right, so now if we go ahead and add these together, we're going to need a common denominator. So we're going to need to multiply top and bottom here by sine x, and top and bottom here by cosine x. And then that's a Pythagorean identity. And then that's 1 over cosine x, 1 over sine x. If we just do reciprocals, flip them up as their reciprocals, we're going to get secant x, cosecant x. Check. All right, 5.5, we're going to focus this part on the multiple angle part. Our double angle formulas, watch out. So this is sine of 2u is 2 times sine u times cosine u. That is only for sine 2u. There is not a similar one for the sine of 3u. It doesn't work that way. Cosine of 2u, you've got several different options. Cosine squared u minus sine squared u, and then if we kind of do some Pythagorean identity work, also works out to be cosine squared, 2 cosine squared u minus 1, or 1 minus 2 sine squared u. So it really depends on the information that you have, which of these you might want to use. Tangent of 2u is 2 tangent u over 1 minus tangent squared u. So those are our double angles. Right, so solving a multiple angle equation. So here, we might be able to change this into cosine squared x by Pythagorean, but the problem is this one's not cosine x. This is cosine 2x. So maybe that's where we want to focus. Kind of looking back over to here, we could use any one of these. Now, since our problem, the rest of our problem is in sines, I'm kind of thinking we should use this one. So let's replace this with 1 minus 2 sine squared x. Now we can combine like terms. It's already equal to 0. We get sine squared x is minus 1 equals 0. In this case, yeah, we could factor, or we could just do this as a square root method problem. Just don't forget plus or minus. We square root both sides. Sine x equals positive 1 or negative 1. All right, so where's sine? Where's our y coordinate? 1, straight up. Where is it? Negative 1, straight down. So we could, in a sense, think pi over 2 plus 2n pi, or 3 pi over 2 plus 2n pi. Or we could just go one of them and just add pi each time. That's probably the most efficient way to go. Pi over 2 plus 1n pi gets us to here, and then another pi gets us to there, and that's going to hit all of them. So since they're equally spaced, we could just go plus the 1n pi, n is an integer. Checkpoint, go ahead and pause here, see if you can solve this equation, and again, find all solutions. And the double angle for cosine of 2x, we could go 2 cosine squared x minus 1, since the rest of the problem was cosines. And then just reorder it, factor it. Cosine x equals 1/2, cosine x equals negative 1. And we don't have to get this fancy. We could go with, for the 1/2, you could go pi over 3 plus 2n pi. 5 pi over 3 plus 2n pi, pi plus 2n pi. But in this case, they're all equally spaced by 2 pi over 3. 2 pi over 3, 2 pi over 3. So we can just use 1 and just add the 2n pi over 3 and hit all of them. Don't forget that n is an integer. Example number 2, again, more double angle. Use what we know to find sine of 2 theta, cosine of 2 theta, tangent of 2 theta. Okay. So remember that sine of 2 theta requires that we know sine of theta and cosine of theta. So maybe we can kind of do a sketch. We do know tangent of theta is 8 over 15. And this information tells us we are in quadrant 3. So we're going to want to make our sketch in quadrant 3. And that's going to mean that opposite would have to be -8 and adjacent would have to be -15. Go ahead and pause here, do the Pythagorean theorem to find our missing side. And we get 17. So for sine of 2 theta, 2 times sine theta times cosine theta. Sine of theta, according to our picture, because this is for theta, is -8 over 17. So don't replace theta with that. Replace sine of theta. 2 times -8 over 17 times the cosine, -15 over 17. Let's go ahead and multiply that out. 2 times numerator equals denominator times denominator. We get a final answer of 240 over 289. All right, we got lots of options here for the cosine of 2 theta. You can pick any one of them. They're going to get the same answer. Since we already know now sine and cosine, go ahead and use that. So cosine theta, here's our cosine. We've got to square that minus square that. So 225 minus 64. So 161 over. And then for tangent, since we know sine of 2 theta now, and we know cosine of 2 theta now, we don't actually have to use the double angle identity for tangent. If we trust these, we can use the quotient identity. The tangent of 2 theta is sine of 2 theta over cosine of 2 theta. This divided by this, remember that our denominators will cancel, so we're going to get 240 over 161. 240 over 161. That's it for today. I'll see you next time.